Chapter 12, Developing Strategies for Multiplication and Division Computation. Third grade students should fluently multiply and divide within 100. Fourth grade, multiply a whole number up to 4 digits and a whole number quotient for up to a 4-digit dividend with 1-digit divisors. Fifth grade, fluently multiply multi-digit whole numbers and find whole number quotients with to 4-digit dividends and 2-digit divisors. Useful representations to determine how many oranges 6 classes need. If there are 34 students in each class, students can model 6 sets of 34. If the problem is about a rectangle's area, 6 by 34, then use some form of array. Some students might see 6 groups of 34 and double 34 to get 68, and you have 3 groups of 68 to get 204. Some students might see 6 times 3 and 6 times 4. 6 times 3 is 3 tens, 6 times 4 is the 4 ones, 6 times 3 is 180, and then you add the 6 times 4 in, to make, which is 24, to make 204. Complete number strategy. Students may list long columns of numbers and then add them up. To fade this process, encourage students to recognize that if they add 2 numbers, the next 2 will have the same sum, and so on. Doubling capitalizes on the distributive property whereby doubling 47 is double 40 and plus double 7, and the associative property in which doubling 7 tens, or 7 times parentheses 7 times 10, is the same as doubling 7 and then multiplying by 10. Partitioning by decades is the same as the standard algorithm, except the students always begin with the largest value, such as 27 times 4. They break 27 into 20 and 7. 4 times 20 is 80. 4 times 7 is 28. Add them together, you get 108. Another strategy is to compute mental with multiples of 25 and 50 and then add or subtract a small adjustment. For example, 27 times 4 is changed to an easier one, and then they find an adjustment or compensation is made. So 27 plus 3 is 30. 30 times 4 is 120. 3 groups of 4 equals 12, so you subtract 12. 120 minus 12 is 108. Another one is half then double strategy, in which one factor is cut in half and the other factor is doubled. Split 250 in half and multiply it by 10. So instead of 250 times 5, you have 125 times 10 to get 1,250. As students move from single-digit to 2-digit factors, there is a value in exposing them to products involving multiples of tens and hundreds. The figure on the right shows 3 different problems. Kenneth's work shows how he is partitioning factors 12 into 3, 2, and 2. Brianna is using complete number strategy. She may need to see and hear about the strategies other classmates developed to move toward a more efficient approach. Nick's method is conceptually very similar to the standard algorithm. As students like Nick begin partitioning numbers by place value, their strategies are often like the standard algorithm, but without the traditional recording scheme. One approach to multi-digit multiplication is called cluster problems, or sometimes called strings. This approach encourages students to use a series of facts and useful combinations they already know in order to explicitly guide students in figuring out more complex computations. 34 times 50, students might use these clusters. 3 times 50, 10 times 50, 34 times 25, 30 times 20. In this case, students make an estimate of the final product before doing any of the problems in the clusters. In the cluster for the 34 times 50, 3 times 50, 10 times 50 may be helpful in thinking about 30 times 50. The results of 30 times 50, 4 times 50 combined to give you 34 times 50. It may seem 34 times 25 is harder than 34 times 50. However, If you know 34 times 25, double the answer to get the desired product. Cluster problems help students think about ways that they can decompose numbers into easier parts. The standard algorithm can be the most challenging of all the 4 algorithms of multiplication. The area model. Start with a context and give students a drawing of a rectangle garden of 6 centimeters by 47 centimeters and ask them what the area of the garden is. In the figure, the rectangle can be sliced into separate parts, one being 6 ones, one being 7 ones, or 42 ones, and the other is 6 ones by 4 tens, or 24 tens. Notice that the base 10 language, 6 ones times 4 tens equals 24 tens. Tell how many 10 pieces are in the big section. To say 6 times 40 equals 240, it is also correct, and to tell how many units or separate square centimeters are in the section. The area model, which can be thought about as a connected array, uses rows and column structure to automatically organize each group equally and offer a visual demonstration of the commutative and distributive property. This area model can be also linked to successful representations of the standard multiplication algorithm. 47 by 36 is separated into 4 different squares. A large area of hundreds, 2 small areas of long tens, and 1 ones. And the ones you go 6 times 7. And the bottom tens you go 40 times 6. And the top tens you go 30 times 7. And then the hundreds, the largest area, is 40 times 30. And then you would combine all of your answers. In the open array, you take a blank rectangle and break it up into 4 separate rectangles. Put your numbers where they belong. So we'd have 36, which is broken down to 30 and 6, and 72, which is broken down to 70 and 2. 70 times 30 would be 2100. 70 times 6 is 420. 2 times 30 is 60, and 2 times 6 is 12. You add all 4 numbers up to get 2,592. To help students develop a record scheme, provide multiplication record sheets with base 10 columns on which students can record problems. Partial products from area models. The progression to record a partial product with a 2-digit multiplier is relatively straightforward. Rectangles can be drawn on base 10 grid paper. Full-size rectangles can be covered with base 10 materials, or an open array can be used. In the figure 36 times 47 is illustrated. You have 30 times 40 in the base 10 language, which is 3 tens times 4 tens equals 12 hundreds. The results tell us how many is in that piece in the hundreds section. Avoid saying 3 times 4, which promotes thinking about digits rather than numbers. It is important to stress that the product of tens times tens equals 100. Also in the figure, it shows the recording of the 4 partial products in the order of the standard algorithm, and how these products can be collapsed to 2 lines if small digits representing the regrouping are used to record the trade. In number 1, you would take 783 and 5, because 4 friends plus themselves, and you're going to break the 700 up into 7 separate hundreds, and each person is going to get 100. So you have 200 left, 2 separate 100s. So you break that up into 5 separate. Each group gets 40 of that 200. Then you have the 80 tens. You break that up into 5, take away 5 tens from 80. Each person gets 5 tens. Each person gets 1 set of 10. And there's 30 left. Then you break 30 up into 5 separate groups. Each person gets 6. So each person is going to get 156 pennies. There's 3 pennies left over. Number 2, repeated subtraction. You're just going to take 625 minus 20, then that number minus 20, then that number minus 20, until you end up with less than 20 peanuts. In illustration A, 72 divided by 3 using base 10 materials in the sharing process. When no more 10s can be distributed, a 10 is traded for 10 ones. Then the 12 ones are distributed, resulting in 24 in each set. The direct modeling approach with base 10 materials is easy to understand. Illustration B shows that the problem 342 divided by 4. The person sets out base 10 materials and draws a 4-column recording chart to match the divisor and the image of the paper plates that had been used previously on an organizational tool for sharing. There isn't enough hundreds for each child, so the person splits 2 of the 300s in half, putting 50 in each of the 4 columns. That leaves this person with 100, 4 10s, and 2 1s. After trading the 100 for 10s, now there's 14 10s. The person gives 3 10s to each child, recording 30 in each column. And the person then left with 2 10s and 2 1s, or 22. 4 times 5 is 20, so each person gets 5, leaving 2. The person splits the remaining 2 pieces in halves and write half for each column. Figure C. How many bags with 6 stickers in each can be made if there are 164 stickers? The person wants to find out how many groups of 6 are in 164. As the first step, she estimates and tries 6 times 20 by multiplying 6 times 10 and doubling the answer. Then the person tries another group of 10 and recognizes that is too high. She knows that the answer is more than 20 but less than 30. The person thinks about how many 6s are in 44, which is, she knows, is 7 and 2 left over. So her answer is 27 bags with 2 stickers left over. In figure C, the person is solving a division problem that involves measurement situations. How many bags with 6 stickers in each can be made if there are 164 stickers? The person wants to find out how many groups of 6 are in 164. She estimates that 6 times 20 by multiplying 6 times 10 and doubling the answer. Then she tries adding another group of 10 and recognizes that is too high. She knows that the answer is more than 20 but less than 30. She thinks about how many 6s are in 44, which is, she knows, is 7 and 2 left over. So 27 bags with 2 stickers left over. In the first example, 400 divided by 4 could easily replace 100 times 4, and 125 times 4 replaces 500 divided by 4. The idea is to capitalize on the inverse relationship between multiplication and division. Cluster problems provide students with a sense that problems can be solved in different ways and with different starting points.